In this video, let us talk about the applications of the differential, and one of them is to approximate values. So approximation. So let's solve problems which involves approximation using the concept of the differential. So we have here the first problem. The edge of a cube is 15 centimeters. Find approximately, by using differential, the increase in surface area if the edge is increased by 0.02 centimeters. Again, we are going to find the increase in the surface area of the cube if the edge is increased by 0.02 centimeters. So first, let us try to draw a cube. So supposing this is our cube. Say we let S be the edge of the cube. Now, the edge of the cube is 15 centimeters. And we are to find the increase in the surface area if this edge is increased by 0.02 centimeters. So S is 15 centimeters. But if it is increased by 0.02 centimeters, that would mean that ds is equal to 0.02 cm. So we can compute for the surface area of the cube using the formula. So if you don't know the formula of the surface area of a cube, just remember that the surface area is the total area of the entire cube. So we know that there are actually 6 faces of a cube, and each face of a cube is a square. And what is the area of each square? It's s squared, right? So s squared. But then there are 6 faces here, which means that the surface area is equal to 6s squared. So when this s, edge of the cube, changes, there is a corresponding change in the surface area. And that is what we are looking for. Find approximately, by using the differential, the increase in surface area of the edge if the edge is increased by 0.02 centimeters. So meaning the change in the edge is very, very small. So that would mean that there is a corresponding change in the surface area which is also very small. So we compute by finding the differential. So the differential of the surface area is equal to 12s ds. And so since s is 15 centimeters and the change in the edge, the increase in the edge, is 0.02 centimeter, then we can find the approximate change in the surface area of the cube. So we multiply 12 times 15 times 0.02, that would give us 3.6 square centimeters. For the next problem, a cylindrical hole with a diameter of 3 inches is drilled through a metal plate 2 inches thick. It is desired to drill again the hole in order to increase its diameter to 3.1 inches. Find the approximate volume of the metal removed. So meaning there is already a cylindrical hole. So if we try to draw this, for the top view, well, we already have this hole. The diameter is 3 inches. So if we draw the diameter here, this, let's say we use the variable capital letter D for that, that's 3 inches. Now, it is desired to drill again the hole in order to increase its diameter to 3.1 inches. So we drill again. Drill again such that the diameter, so let us draw this again, this is 3 inches. But now the new diameter is 3.1 inch. This is the 3.1. So this is just for the top view, no? So if we draw the cylindrical hole, this would be the original hole. And then after drilling again, there would be a bigger hole now. But remember that the height of the metal plate does not change. The thickness here is given. The thickness is 2 inches. Okay, it's 2 inches thick. So what changed here is just the diameter. So originally the diameter is 3 inches, but there is a change in diameter, a small change in the diameter. So if the new diameter is now 3.1 inch and the original diameter is 3 inches, then our small change in the diameter is 0.1 inch. Now because there was a change in diameter, so there was a change in the volume of the metal removed. Now our volume, formula for volume of a cylinder, V, is equal to pi r squared h. And remember that this h is constant. It's 2 inches, so we can just replace that with the value. So V is equal to pi r squared times 2, or that would be 2 pi r squared. So finding the differential dV. Okay, so this is a small change in the volume of the cylindrical hole when there is a small change in the diameter of the hole made. So 4 pi r dr. But we have diameter. So instead of using the radius, we can also make this or express this in terms of r. Or you can just find the dr. It will still give you the same answer, diba? Because d, the diameter, is just twice the radius. So you can use the radius or you can use the diameter. So what would be the formula of the volume of the cylinder if we will be using the diameter? So that would be pi radius is actually the diameter divided by 2 quantity squared times the height, which is 2 inches thick. So that's 2 pi times d squared over 4. So therefore the volume here is equal to 1/2 pi d squared. So finding the differential of the volume, that would give us pi d differential of the diameter d. So the original diameter is 3 inches and the differential is 0.1. So the differential in the volume, or the approximate volume of the metal removed, is 3 pi over 10, what's the unit here? Cubic inches. Alright, next problem. We are to evaluate the cube root of 63 approximately using the concept of differentials. Now remember, we recall for a function, for f of x equals y, and if there is a change in x, there is a corresponding change in y. So delta x, there is a corresponding change in y, delta y. But if this delta x is very, very small, that would give us dx. There is a corresponding change in y, which is dy. It's not delta y anymore. And remember that delta y is not equal to dy. So if this delta x is very, very small, this will now be f of x plus delta x equals y plus dy. Again, this dy is not equal to delta y. Now, if we are to extract the cube root of 63, the first thing that we determine or write would be that this is our cube root of 63 is our f of x plus delta x, wherein the delta x is very, very small. So we write that as cube root of 63 is equal to y plus dy. Okay? So that 63 is equal to x plus dx. Okay? After that, we think of a number that is closest to 63 because we are extracting the cube root here. We think of a number that is closest to 63 that is a perfect cube. A number that we can extract a cube root, and that is 64. That would be our x. Okay? That would be our x. So 63 is equal to 64. So if x is 64, then what would be dx to give us 63? It would be negative 1. Okay? So our x is 64 and our dx is negative 1. So that for our function y therefore is equal to the cube root of x. So finding the differential, dy is equal to 1/3 x to the power of negative 2/3 dx. So when x is 64, dy is equal to 1/3 64 raised to the power of negative 2/3 times negative 1. X is 64. Also, dx is equal to negative 1. That would give us dy equals negative 1/48. So we already have our dy. We just need now to solve for y. So solving for y, when x is 64, what is the value of y? So y would be equal to the cube root of 64, and y therefore is equal to 4. So we now have dy, and we now have y. We can now solve for the cube root of 63. So therefore, the cube root of 63 is equal to our y, which is 4, plus our dy, which is negative 1 over 48. So 4 minus 1 over 48. That would give us 191 over 48, or that would be approximately equal to 3.9792. So if we use our calculator to extract the cube root of 63, it would be approximately equal to 3.979.